Welcome to this webisode for separation processes. I'm going to run through the solution to assignment 5. So the question statement is given here. The table on the right hand side shows the experimental data for adsorption of water vapour from nitrogen in a packed bed of molecular sieve. The depth of the bed is 0.88 of a foot, the temperature is 83 degrees Fahrenheit, pressure is 86 pounds per square inch absolute. The entering gas velocity is given as a molar flux, which is 29.6 pound moles per hour per square foot. The water content coming in is 1,440 parts per million on a volume basis. The initial adsorbent loading is 1 pound of water per 100 pounds of the molecular sieve, and the bulk density of the bed is 44.5 pounds per cubic foot. For that entering gas moisture content, which is 1,440 ppm, the equilibrium loading on the bed is 0.186 pounds of water per pound of the molecular sieve. We're asked to determine the bed height required for a commercial unit, so for a different column operated at the same conditions, so that the exiting gas has no more than 9 ppm by volume and a breakthrough time of 20 hours. So if we draw a quick diagram, there's our packed bed with the flow rate and concentrations shown on it. The key assumptions for solving this problem are that the edge effects are negligible, so that the behaviour we see on the smaller column is replicated in the larger column, and we assume ideal gas behaviour for the water vapour nitrogen mixture. The first step in our analysis is to calculate the height of the bed required. So remember, this is not the total height, but just the height of the bed, and we use this equation to do that. The terms here are the feed concentration, the feed flow rate, a volumetric flow rate, the breakthrough time, the adsorbent loading capacity of that feed, the bulk density of the bed, and the cross-sectional area of the bed. And it doesn't really matter what units we use for each of these terms, as long as they're all consistent. The first step is to calculate the feed concentration, and we do that. It's 1,440 parts per million. We can equate that to 1,440 pound moles of water vapour per pound mole of the total gas mixture, and then just multiply it by the molar mass of water. So we get 2.59 by 10 to the minus 2 pound moles of water per pound mole of the total gas mixture. We don't actually know the cross-sectional area of the bed A, but we are given the ratio Q divided by A, which is G, in the problem statement. So with those values, we can then substitute into our expression for the height of the bed with the other known values, and we calculate a value of 1.96 feet. So I've written that out with all of the units for all of the terms here, so you can check that they all cancel out. So the feed concentration is pounds of water per pound mole of gas mixture. The mass flux is pound moles of gas per hour per square foot. Our breakthrough time for the commercial column, which is what we're calculating the height of the bed for, is 20 hours. The loading capacity of the adsorbent, the equilibrium loading capacity was 0.186, but when the feed entered the bed, the adsorbent already carried 0.01 pounds of water per pound of the molecular sieve. So we actually need to adjust that value to reflect the actual loading capacity of the adsorbent, and this is the density of the bed, 44.5 pounds of solid per cubic foot. So if you cancel all that out, everything cancels except for foot to the power of 1, which is 1.96 feet. The second step in the analysis is to calculate the height of the unused bed. So there's a few steps to that. First one is to plot the curve so we can see what it looks like, and then we need to calculate the time for the used bed and the saturation time, or the total time. And we do that by evaluating these two integrals. So the time that's used up at the breakthrough condition is given by integrating the distance between this curve, where C over C naught equals 1, the difference between 1 minus C over C naught dt up to the point of the breakthrough curve, which is just here. So that's this integral here. This integral is the total area between 1 and that curve, between 0 and infinity. With those two values and this formula, we can calculate the height of the unused bed. In this case, it's the height of the unused bed in the laboratory scale column, since we were given the total height of that column, and we know that the height of the unused bed will be the same on the commercial column. So to evaluate those integrals, the easiest way to do it is to do the integration numerically in a spreadsheet. So here's the graph from the previous slide. What we have here is the information that was given to us in the problem statement, the ppm measured at the exit from the bed and the time corresponding to each of those measurements. This value C over C naught is just normalizing the concentration by the feed concentration, which was 1,440. Then I've created a new column here, which is 1 minus C over C naught. So it's just 1 minus whatever value is in that column to give us this column here. This column here is where we do the numerical integration. So this segment dt is the difference between the time point here and the time point here. So that's how that is calculated. 8.8 minus 0 gives 8.8. Likewise for the next one here, 9 minus 8.8 gives 0.2, and so on. So this corresponds really to the width of a thin slice in our integration here, although the first slice is rather thick at 8.8 hours. And then we simply multiply 1 minus C over C naught by dt. So what I've actually done is averaged these two values here, so taken the mean of these two and then multiplied it by the thickness. This is the equivalent to using the trapezoidal rule. So when we take that integral and add it up, if we add up all of these, the area of all of these slices, we'll get this total sum here, which is in fact the value of T saturation or T total. And if we add up everything from 0 to 9.4 hours, which was the breakthrough time, we get the time used up at breakthrough condition is exactly 9.4. The reason those numbers are so close to each other is because the breakthrough condition is set relatively low, and so when the breakthrough condition is set relatively low, the area between this curve and that curve can be approximated by a rectangle. So that's why they're effectively the same. Substituting those values into our expression, we can calculate the height of the unused bed as 0.12 feet. So then it's very straightforward to calculate the total height required, which is 2.08 feet, and we can express that as a statement here.